Our topics in 4.6 are linear approximation and differentials. These two topics are related, but we're going to try to keep them separate, at least in the beginning, so we can see which one's linear approximations, which one's differentials. We're going to begin with linear approximation. The first thing we're doing is we're actually going to take a look at this graph right here of this function, and I've got it graphed in another window on Desmos, and it asks us to zoom in around the square root of 2, so I plotted that point right there. So if I zoom in close enough, like the point, to that point, what we notice is that the function starts to not look like a curve anymore. It starts to become like a line. It looks linear. Right? It looks pretty much like a straight line right here. I might be able to find its slope, its y-intercept. It's definitely looking more and more linear the more I zoom in. And that's the idea of linear approximation. If you're close, whatever close happens to mean, if you're arbitrarily close to a value, you can predict the y values of the function around it by using a linear function, linear approximation. These values do look like they would fall in a line. That's the idea of linear approximation. Okay, so describe what we notice as we zoom in. Okay, it begins to look linear. So if we zoom in enough, it looks more and more like a line. And this leads us to the idea that we can reasonably approximate any differentiable function over a small enough interval with a line. And that's going to give us the definition here of linear approximation. So the first thing I want to do before I actually talk about linear approximation is down below, talk about what a line looks like in its equation form. So we've used lines before in point slope form. Remember that point slope form is y minus y1 equals m times x minus x1. And we know that we can approximate the slope with the derivative, or we can get the slope from the derivative. So if we have f prime at a, that can give us the derivative. And then if our point instead of x1 comma y1 is just a comma f of a, then this would look like f prime of a times x minus the a coordinate equals, again, y minus the y coordinate is f of a. And so this is just a regular equation of a line here, and so if I solve it for y is going to be f prime of a times x minus a, and then we can add the f of a to the other side. So this is just an ordinary line where we substituted an ordered pair instead of x1, y1, calling it a, f of a, and then since the function is f, I know that its slope is going to be f prime of a. Okay, so just as a note that that's what this is. Like we've called it, instead of y right here, we've called it L of x, but this is our linear approximation. See, f of a plus f prime of a times x minus a. So instead of having to memorize or remember this new special magical formula for a linear approximation, it's just a line, right? It's just a line. And so that's where it comes from. But the linear approximation is going to be the line that goes through your point a f of a and has slope f prime of a. That's all it is. And so it's a tangent line. We've done those plenty of times before. Another way to say it, this is just a tangent line. It's just saying what we're going to be using is the tangent line to do our linear approximation. So if we're going to make a linear approximation, we'll find the tangent line to the curve at a point and use it to approximate the y values. Okay, so let's do this on the next page. We've done tangent lines plenty, so this should be familiar. We've got a function here. We're going to use the square root of x, find the linear approximation function at x equals 1. That's the same thing, of course, as finding the tangent line at x equals 1. So we've done that a lot. So just as a note, this is the tangent line. Why does it have a different name? Well, it just has a different goal. To me, we're going to use it for it differently than I used it before, but it's the same function. So the first thing we'll find is, for part A here, is the derivative. So f prime of x is going to be 1/2 x to the negative 1/2 power. And so I really want that evaluated at 1. So f prime of 1 is going to be 1/2 times 1 to the negative 1/2 power, which is 1/2. I also need the y value, so if I take the original f of 1, I get square root of 1, which is 1, so the original ordered pair was 1, 1. So the linear approximation function, L of x, is, remember that's the y value, is f of 1, that's 1, plus slope, 1/2, times x minus the x coordinate, which is also 1. So 1 plus half of x minus a half, just writing it in terms of a line, it is 1/2 x plus 1/2. Okay, that's our linear approximation function, aka the tangent line to the graph at x equals 1. Okay, so we've done that part of it plenty of times. Now we're going to use the linear approximation to estimate the value of 1.1. Okay, now I would not be able to take the square root of 1.1 in my head, but I can plug 1.1 into this linear approximation function. So we're going to use the linear approximation function, part B here, and what we want to do is find an estimate for the square root of 1.1. It's going to be approximately L of 1.1, since L approximates the square root of x function, right? So what we're making is an approximation that f of x is approximately L of x for x near 1, because 1 is the goal that we've chosen here. If, of course, we wanted to change where x, what x was near, we'd have to change the L of x function, right? It's built for x near 1 in this case, because I've plugged in 1 for the x coordinate and the f of 1 for the y coordinate, and as well, that's the slope specifically at 1. Okay, so this is going to be equal to 1/2 of 1.1 plus 1/2. So I could use a calculator, but I think we can do this in our head as well. Half of 11 is 5.5, so this is 0.55 plus 0.5, so it is 1.05. Okay. Now compute the magnitude of the error by getting the actual value. So in part C, we can get that actual value of the square root of 1.1. It comes out as 1.048, so we're really close. And so the magnitude of the error, we're just going to subtract those two things. So minus 1.05. Magnitude just means unsigned, so we won't use the negative. So I'm going to write down real quick that the square root of 1.1 is approximately 1.48 something. Hang on. If I cut that, it was 0.048. Right, 0.48. 8. 1. Okay. So now we have the error is approximately 0.00119. So it's a pretty small error. Okay, and I didn't put this negative with it because it says the magnitude of the error. Magnitude up here is another word for absolute value, so positive only. All right, now part D is going to ask us how would this error change as we were approximating the square root of 1.2, so we're going to find L of 1.2 instead. So that's 1/2 of 1.2 plus 1/2, so that should be 0.6 plus 0.5. That is 1.1. That's the approximated value, not the error. So let's go find the error. Over here, so if I did the error of from the square root of 1.2 minus what I got for the prediction, 1.1, I have an error of about 0.00455. Okay, so as we notice, since the value that we chose was x equals 1, the closer that we are to 1, the better our predictions are. If we start getting far from 1, even past 1.5, we're going to have quite a lot of error. Very, very close, we have little error. 1.1, 0.001 is a very small amount of error. 1.2, 0.0045, a little more error, but it's still insignificant. But as you get further and further away, that error is going to get very, very large. So the linear approximation is by using tangent lines to use linear functions, which are much easier to solve than the actual square root function. So you can get them to be done with computers and in your head as well.